Let's see. Continue. So we were understanding the you call the multiplicative weight update method algorithm. So this was the algorithm that was basically we analyzing this, the opinions of the various experts and go along. The way the multiplicative weight update method does it, you started off with a uniform weight on all experts. You started off with an average. You picked a expert based on this on a probability distribution in which the probabilities are proportional to the weights. And then you kept updating the weights and the main based on their outcomes. If the expert got it very lossy, you scale the weight by 1 minus epsilon. If it did not lose anything, you didn't update the weight at all. And for this one, we also added a gain portion of also. If the MIT was -1, you actually incremented its weight. And we saw an analysis of this. A couple of places where I had to prove left some inequalities on one. We'll see that today. And we eventually proved this result. That is, at the end of T steps, the expected cumulative loss of the algorithm is at most, there's a ln n over epsilon, which is just to find out which expert you're into, the initial loss. Then it's at most the loss of any single expert's loss, cumulative loss, and plus epsilon times this extra factor. That was what we had. So basically, MTs were all non-negative. This is just 1 plus epsilon. We got rid of the 2 which was there for the deterministic thing. We have a thing which gets almost the loss of the best expert in hindsight with an additive parameter of log n. Okay. So the thing to notice about this is because we got this for every expert, we actually also got the following statement. The following statement also follows from one. At the end of T steps. So typically, we were comparing our performance with a fixed experts for the works, but you could also have compared. So we were comparing LT versus there was a ln n by epsilon plus. I want to claim you don't even have to compare the fixed expert. You could have compared with, this is an obvious fact, and PB any fixed distribution on the experts. This is a distribution doesn't change with on the n experts. Then you fare well even compared to this distribution. It is T. Epsilon. That's just got back by taking a convex combination of the previous result. And the key thing over here is the fact that P is fixed. P is not something that is changing as the key over here is the fixed part. We will see slight modifications of this algorithm.
Positive.
The
first term is where the NPs are positive and the second term is
No. So this is a modification. This is empty. This is the losses of, if you had worked with this probability distribution, that's the loss you will see. That's the cumulative loss you will see over time. This is just, I should possibly mention this, what you see this, right? Where this vector, and when I mean by empty, I mean just the absolute values of MT1, MT2, MM. It's the absolute values. It's the same vector, but term by term, I'm taking an absolute value. The first observation will be something called the hedge algorithm. So some people in some textbooks you would find the hedge algorithm instead of this algorithm, and the key difference is in the update rule. So notice the MWUM update rule was WIT plus 1 got replaced with WIT got replaced with 1 minus epsilon MIT. And then later on in the proof, we actually, the first step, in the early steps of the proof, we use that this is, we approximate with E x per E per minus epsilon MT, to recall. Let's just look at the proof. So at one step in the proof, somewhere early on in the proof, over here we had this, we were computing phi t plus 1, we had written this expression, and then we sort of did this. It's an inequality. We're just using 1 minus x is less than or equal to e power minus x. The hedge algorithm keeps the update rule as this object instead. The key difference is that's the hedge algorithm. The difference between the two of them being this fact. And you can analyze it exactly as we did. And here the final conclusion for hedge would be the same. This is the hedge. T, the same as ln n epsilon and in fixed distribution P. So instead of an absolute value, you get an empty square. That is, this is the vector in which you replace every quantity by the square of the quantity and then take the dot product. And the proof of this is identical. Except I think in one place we'll use the fact that 1 plus epsilon power x is less than, rather you just, we'll use the fact that this is less than 1 minus epsilon x. We'll use this fact. Sorry. E power minus epsilon x. X to e power minus epsilon x is less than or equal to this. You will use this somewhere along the proof. Otherwise, the proof is identical. What I want to now show is suppose a different, suppose equation 1, equation 2. Suppose set of allowed probabilities is not all possible.
Shouldn't inequality go other way?
Once again, I'm missing the equality. So we'll be doing the same.
If the minus x is, there will be minus Actual square x square by 3 factorial. So
And one place in the proof you'll use that inequality. That would be the inequality. All possible distributions. Right now, this is a weird. Right now, it seems strange. What it means that is the algorithm is acting according to some probability distribution on the experts. It's taking some. There might be settings. We will see one of them. Not possibly, not in today's lecture. Possibly not in Monday's lecture. Also, possibly in next Thursday's lecture. We'll see an application. The question is, you can't just update the weights and use that probability distribution. You'll have to do something else. So let's assume. So suppose, so what is the all possible probability distributions? All possible probability distributions on n experts. This is basically the simplex. What do I mean by that? This is this area delta n, which is set of all p1, p2, pn, such that the pi's are all greater than or equal to 0, and the summations of pi is equal to 1. That's a set of all possible. And so far, we are just each time the algorithm is acting according to something in this set. This is the simplex. So think of this as this is simplex. But suppose you are allowed, suppose the allowed distributions is only some set P, which is a subset of delta n. And let's assume P is a convex closed set. Certainly it's closed because it's in a closed set. Delta n is a closed set. It's in a convex closed set. So the simplex is something like this. You have the simplex out here, and this is some P. That's the allowed set of probability distributions. So you can only act according to one of the probability distributions here, but the update rule might push you somewhere outside. What do we do? Typically, you just pick. What we try to do is we pick the thing which is close probability distribution over here, which is closest to what the update. Say the update rule picks you at some point here. We'll find a point here which is closest. Now I have to define under what metric you're closest. And then the metric we are going to use is we are going to use relative entropy. So if P is not in P, we'll pick, or rather P hat is not in P, pick up distribution P that is closest to P hat in the set P. And for the notion of closest, we can use different things. The one that seems most convenient for this is in terms of relative entropy. Huh?
P hat not in P, or is it P hat in?
Sorry, if P hat is not in P hat is not in, pick a distribution P that is closest to P hat in P. And have you guys seen what relative entropy is? So relative entropy is this, it's not actually a distance, but it's a nice way of measuring how different two distributions are. So let's spend a little time understanding one. So suppose you're given two distributions. P is one distribution on n elements, P1, P2, Pn, and Q is another distribution on n elements, Q1, Q2, Qn. Then the relative entropy, Re of P versus Q, sometimes also called the divergence, or sometimes also called the Kullback-Leibler distance, named after the people who defined it, is defined to be just summation Pi ln Pi over Qi. So some nice things about, so some observations, these are not observations, these are each of them require a proof, but we will take it without proof for now, is for all P and Q, the divergence between the relative entropy between P and Q is always a non-negative quantity. This is a consequence of convexity. We can write it down, we can prove it, but I will take it without proof for now. You can show that expression, as long as the P's are a probability distribution, Q's are a probability distribution, if you do that summation, that will always be a non-negative quantity. 2 dp q is 0 if and only if P is identical to Q. The two distributions have to be identical. 3, this is not dpq is not equal, it's not a symmetric measure. So it's not like the usual notion of distance. Distance is usually a symmetric measure between the two distributions. This is not symmetric. And that you can see by the asymmetry in the definition itself. Notice this can become infinity. When can it be infinity?
When the key was, any of the key was 0.
If the Q distribution puts 0 weight at a point where the P distribution puts non-negative weight, puts positive weight. If it was 0 by 0, then it's by convention that I'm going to 0 non-0 by 0, I'm going to assume it to be 0. It's only when P puts weight on P puts a positive weight on something which Q puts no support. Basically, if the support of P has to be fully contained in the support of Q for this to be a finite quantity. Otherwise, this can shoot off. That's one thing. The fourth and the most important property for us will be this notion of Bregman projection. You have this convex set P, and I have some Q distribution which is outside the set P. What I want to find is a P. Let's find a consistent with what I'm going to keep later. Let's call this P hat. So I'm going to put this to be P star. P star is the argument over all P in P, which are going to minimize the relative entropy between P and P hat. This P star will define this object, will define it to be the projection of P hat in the set P. Okay. So among all P's over here, you take the one which has the least relative entropy with P hat. The nice thing about this, the property about this is this projection satisfies a Pythagorean-like rule. And what do I mean by that? Suppose you picked up some other Q. There was some other Q over here. And you want to compare Q to P hat versus P star to P. Certainly Q to P hat is larger than P star to P. You can in fact show that that's a definite. By definition, that is how you have chosen it. But this P hat, this projection vector, P hat satisfies. You look at the divergence from Q to P hat. This is at least the divergence from first Q to P star plus the divergence from P star to P hat. That in that sense is usual. If it's called Pythagorean because if these are squared distances, this would be an equality. And this would show why that is actually better than it. The projection will always be the projected square. If this was not relative entropy but the squared Euclidean metric, then you would have equality if this was the squared equivalent, because that's the projection is the foot of this one, and you'll have a right angle triangle over there, and hence you'll have such a thing. This is almost the same thing. It gives you the inequality in this direction. By the way, the Pythagorean theorem is what tells you that the projection is the closest vector, because everything else will be greater than this quantity by at least so much. This also has the same property, except it's not an equality, it's an inequality. It works but that's the direction we need to show. So this projection has this property. If you project it, it's going to have this property.
Compute the projection.
So this is a good question. How do we compute the projection? It's a convex problem. So you can appeal to any convex optimization sort of for this one and solve it. Right now, I'm not saying how to do it. I'm not saying how easy it is to compute it. Projection is, so we are going to assume you're given a convex set, you're given a membership oracle to it. We'll see it when we have an application, because there you'll know what you'll see exactly, and we will show that you can actually compute. Given P hat, we'll be able to compute P star for that particular setting. This might not be true all the time. That is, this is a well-defined distribution. The projection is a well-defined operation, and you can define it front. It's unclear how to solve it. At least the examples which we will see, we'll encounter, we'll show you exactly how to compute it over there.
Some other metric also, right?
He could have used another metric. The reason this metric is used, you'll see in the proof, this proof is now will exactly imitate the old proof that we have. And in some sense, this is a nicer metric to work with while understanding the multiplicative weight update method. So this was done in the past, as I mentioned, multiplicative weight update method was something which was discovered and rediscovered in different communities across the years. And each of them tried with different metrics, and finally they realized this was the cleanest metric to work.
Maybe the optimal.
I think this is the cleanest metric to work with. In fact, it's cleaner than it's cleaner to state the final theorem of MWM using this metric rather. So, for example, we could do this metric even when P had if this squiggly P is the entire distribution. That time projection will not do anything. It will just return the same object. Even then, relative entropy happens to be the nicer thing to analyze the algorithm. We so far analyzed it in terms of this potential function that we came up with. So instead of potential function, what we'll see shortly, the nicer thing is to analyze the relative entropy between our current distribution that the algorithm maintains and some target. You have a fixed distribution. You want to compare these two. So actually, that should be the notion. If you had seen this, why did we pick this potential function? It seemed like an arbitrary thing. Or rather, we were inspired by what happened in the weighted majority. There it worked, so we continued using the same thing. But in general, what you want to work as well as some fixed distribution. You want to say, I want to work. So you have the algorithm maintains a distribution P of T, which is constantly updated. You would like to talk of some metric between these two, and then that is used. So usually the standard old proofs used to go with take some metric between these two and see how this metric changes with time. And what this one is stating is actually the nicest metric to work with. What we'll see shortly, we'll see the proof very shortly, is that this metric works. The relative entropy happens to work cleanest with us. And also there's a reason for it. There is this proof, it's a multiplicative thing. So these exponentials are going to keep coming. The metric that works nicely with these exponentials coming is the metric which has logarithms inside it. It works nicely. Certain things commute nicer with it. So I'm going to just rewrite. We're going to incorporate Bregman's projection into the update rule. So what will that be? So So as before, you initialize the starting probability distribution to be the all uniform distribution. This is equal to UN, the uniform distribution. Sometimes this might not be this one. If that's not the case, you initialize it with or some P1 in P. That is, this might not be a distribution you can work with. So you start off with some P1.
So the Pythagorean like property.
Which one?
Pregnant divergence.
Yeah.
There, this. The usual triangle inequality, the direction is opposite, right?
The usual triangle inequality, the direction is off. No, this is not triangle inequality. That's why I didn't call it the triangle inequality for projection. This one. This is true. The triangle inequality is true for any 3 points. This is not true for 3 points. One of the point has to be the foot of the perpendicular. That's why it's called Pythagorean. That triangle has to be a right angle triangle in at least. If it was a usual Euclidean metric, that would have been a right angle triangle. That's why to remember it, it's easier to call it the Pythagorean thing. Then you will get this, and this identity is the one that shows that length is smaller than any other length. So this is not triangle inequality. It's not triangle inequality. Triangle inequality doesn't work so nicely in the relative entropy. This one. It's not triangle inequality. It is the inequality which is used to show that projection is actually better off than any other projection. Any other probability distribution over there. One at that's all right. From entity according to PT B. Yeah, these are all standard. I should have skipped all this. Observe the outcomes. So the outcome vector MT, which is M1T. Update weight true. So PT plus 1 of I is going to be what are we going to do? We are going to make it Pi of T into 1 minus epsilon MIT, but we'll have to scale it up so that it becomes a probability distribution. PT is just something so that this summation turns out to be this one. I think I might have to call this PT plus 1 is what I called it in the past. Let's keep it as PT. Where PT is, let's call this hat because this is not the final thing, where PT is the normalization constant to make Pi hat T plus 1, sorry, P hat T plus 1 into a distribution. Okay. But then this is not P. P of T plus 1 is going to be the projection of P hat T plus 1. And then that's the probability you will use in the next round. So the key difference is basically this is. Nothing's changing over here. This is similar to, this is exactly as before. This is the key change. Okay. So let's analyze. So let's analyze the MWA in terms of this particular. So what we will do, the previous, so this analysis, this will be, so instead of previously, we used phi t as a potential function. If you recall. Now what we'll do is we'll see, we will now instead see how t of p restricted to pt varies as algorithm proceeds. So here P is a fixed distribution that you are comparing against. This could be a distribution that is just focused on one expert. It could be any convex combination of experts, but it's a fixed distribution on the n experts. Here is fixed. So let's try to understand d of p given. Strictly speaking, I should do pt plus 1, but let's do p hat t plus 1 first, minus d of p t. How does this change? How does each step of the algorithm change this? Notice this is summation pi by ln pi by p hat t plus 1. This is also summation pi ln pi by pt I. So I can take the summation common. It's the same summation pi, and the first ln pi will get cancelled out. So this will actually be, this is just going to be summation I over the experts, pi ln, what will it be? It will be pti by p hat t plus 1 I. Is that right? Or I have to have it the other way around? That is right. The nice thing about this one is this exactly measures the update. The update is exactly that ratio that's happening there. So we have pi times ln, what was this? This was this normalization constant goes numerator by 1 minus epsilon MIT. That's the update rule. So PIT is the other, exactly that quantity. Huh? So this is just ln phi, ln pt minus summation pi Okay. And all the inequalities we're going to use are all the same inequalities we used previously. To recall, what was the inequality we used? there was a place where we had to bound 1 plus epsilon MIT. We had bounded it using what? We had to bound this. So if you recall, there was a place in the proof where we had to bound 1 minus eta. We bounded it using x spin minus eta. And which direction does it go? This is less than or equal to this. So if I'm going to use that here, that's in the denominator and there's a negative sign, so the inequality is maintained as before. So this is ln Pt minus summation Pi x puff ln. What happens over here? It's just that goes as x puff minus eta, and I'm just going to get minus epsilon MIT. Is that right? So that's a nice quantity. Remember, this is exactly ln Pt minus epsilon times. This is the inner product between the vector mt and the fixed probability distribution P. Huh? Plus. Let's same time look at what is ln Pt. First, what is Pt? Pt was this summation I Pit 1 minus epsilon MIT. It was this thing to make this normalization 1. I didn't want to do this step over here. We're going to split this up into. We're going to split this up into minus summation I for those i's for which MIT is greater than 0. So that is Pi ln MIT, and then those i's for which it's less than 0, which is Pi ln, what will that be?
We are not following the 20.
Huh?
It is school.
Yeah, we have here, this is going to be 1 by. I'm going to split it these two, and what we will apply is these two inequalities which I hadn't mentioned, which I bungled up last time, which were actually trivial. 1 plus epsilon, we said we wanted to compare this against 1 minus epsilon x when x is between 0 and 1, and 1 plus epsilon x, I wanted to compare it also to 1 minus epsilon x when x is between minus 1 and 0. And which direction will the inequality go? These two. The point is at 0 and 1, these two take the same value. And then it's just convexity. One is a straight line joining those two places. And how does 1 minus epsilon per x look as a curve? Is it below this or above it?
Should be so 1 minus epsilon should be known than.
Which way does it go?
So 1 minus epsilon by should be known than 1 minus epsilon.
And I think both of them go in that same direction. I'm right. That's exactly the inequality that we had done last time. See, let's just see. That's the proof of inequalities. It's these two proofs. It's going the other direction. This is what I bungled up last time. These are just convexity. let's look at it. This is what? 1 minus epsilon power x. This is a quantity less than 1. And you're taking an exponential in it. The e power x is shooting off to infinity starting from 1. This is shooting off from 1, it is going down to hitting to 0 as fast as x goes to infinity, it is going to go to 0. So how does the curve look like of a power x when a is less than when a is between 0 and 1? Certainly at x equals 0, it is 1. And after that, how does it go, Tamper? It goes this way. And this curve is sitting above like this. This is at x being. The inequality is the other way around. You didn't get it right. That's for this one. And the same thing happens for this guy also. This guy is a number larger than 1 minus x. That will also go down this. It's the same quantity. It's a number less than 1. As x goes, it goes. Right. These, in terms of these, what is the, do I want the inequality? What do I want? 1 minus epsilon x. It's greater than or equal to 1 minus. That's quantity. So I'm going to get minus summation ti. What am I going to get? All right. That's exactly what it is. Yes. So for that part, for the greater than 0 part, this is what I get. For the other one, the less than 0 part, I get pi, I get MIT. The MIT comes with a negative sign, which is a bunch of things. Water flow. What was the sign inequality going on here? This was everything kosher so far. Absolute inequalities again. Let's check out the sign of this inequality. Once again, what do I want to show? I want to show. Let's stare at this. I need the inequality to go this direction. And is it going in that direction? Plus. Therefore, the inequalities are all fine. So that's I'm terrible at these. Let's go do this part again. Is this fine? That's, I don't know why I brought in the negative sign there. Ln phi t plus ln 1 minus 1. This one. This I'm just flipping it to the positive part and the negative part. MIT, where this quantity is ln of a number greater than less than 1, number greater than 1. Then I'm going to apply these inequalities. And because it's the denominator, that's the only thing, the inequality flips. So this is actually
1 plus epsilon to the power minus x. It's 1 plus epsilon to the power minus x.
which one? This is minus x.
And x is between minus 1 and 0.
Yes. What is this quantity? This quantity is because of this summation I. This is greater than part pi. Ln of this gets replaced by MIT ln 1 by 1 minus epsilon.
One second inequality will be opposite then.
Second inequality.
Let's take x to be minus half. Then we have the
1 second, no, I should have messed it up again. Possibly this goes 1, 6. So x is going from 1. This is not the curve for this. The curve for this is firstly, these are not the endpoints also, no? These are the endpoints only if second, this is convexity. This is not convexity, and this is not convexity. Let's find out what we want in inequality and then write down what I want to write is the following. I want to write some connection less than 0 pi MIT ln 1 plus epsilon. And does that go in the right direction I want it to go?
the second inequality is reversed. And this follows from Taylor's expansion of 1 plus epsilon.
That follows from Taylor. And Taylor. No,
The quadratic term will be positive.
Yeah, this follows from Taylor. But then does it go the right direction for me? It doesn't go the right direction for me, no? Let's see writing this. The book.
I think since mi is less than 0, they're taking 1 plus epsilon mod mi there.
This certainly that what you're saying is right. 1 plus epsilon minus x quadrat
I mean, if it's just for instance, take x to
Taylor will give you that. Taylor, assuming you can, Taylor is not for rationals. Oh, you can, okay, fair enough, do Taylor around that. 1 plus epsilon x, epsilon square x square. in both directions, I want a lower bound for 1 minus epsilon x. I want a lower bound for 1 minus epsilon x. Minus epsilon x when x is negative. So 1 minus epsilon x is actually claim that this curve goes in the opposite direction. This is right, no? Because 1 second, let's look at this. 1 plus epsilon. You're looking at 1 plus epsilon to the power minus x versus 1 minus epsilon x as x is in -1 to 0. This is the same as looking at 1 plus epsilon to the z versus 1 plus epsilon z versus when the z is in 0 and 1. But then
Side is more than right.
no, it's not. No, it cuts it and then goes up. You're looking at the region between 0 and 1. At that point, the curve is below and then it shoots up. You're looking at only the region between z being 0 and 1. So for z in 0 and 1, 1 plus epsilon x is in fact greater than 1 plus epsilon. Sorry, z is greater than 1 plus epsilon to the z, no? Convexity again. So this curve is going to, the exponential curve is below the line between 0 and 1. After 1, it will shoot up. Therefore, you do have this inequality the way I wanted it. Once again, the first inequality is just convexity of that curve. The second is also convexity, but goes this way. So you have this sequence of equations. Apply the same. The next approximation we'll use is the approximation we had used once again before. Greater than 0. Ln of 1 minus epsilon is its expansion is epsilon plus epsilon square by 2 plus epsilon cube by 3 and so on. So I'm just going to upper bound it by epsilon plus epsilon square. It's just pi mit epsilon plus epsilon square. And this is pi mit ln of 1 plus epsilon is epsilon minus epsilon square by 2 and so on. I'm going to lower bound that one by epsilon minus epsilon square, but MIT is a negative quantity, therefore this direction goes in the fine, right? And here I'm using the fact that ln of 1 by 1 minus epsilon is less than or equal to epsilon plus epsilon square, and ln of 1 plus epsilon is greater than or equal to epsilon minus epsilon square when epsilon is small. With those two together, you get ln phi t plus epsilon times summation I pi mit, that is happens for everybody, plus epsilon square times summation pi mod mit. Similar to what we had. Epsilon phi t plus epsilon into P empty plus epsilon square into the absolute value of T times P. But now let's look at what Vt is. Vt is itself summation PIT 1 minus epsilon MIT. I'm going to upper bound this as the summation over I. PIT X spin. Okay. Go to the norm now, the norm after. Let's do the ln first. Let's take the ln of this quantity. Ln of Vt. Perfect. Now I just apply the fact that 1 minus epsilon x is less than x spin minus epsilon x. So this is just minus epsilon empty. So putting all this, what do we get? We get the divergence. Yeah, this is fine. Sorry for all of this. It's P to P hat T minus D of P to PT is less than or equal to. This was a less than or equal. Epsilon MPT minus MTPT plus epsilon square into
That means P is P have P plus 1.
yes, this is D. Okay. This statement is very insightful. Why is this insightful? What is this quantity? This is the loss of the algorithm at the teeth step. What is this quantity? Sorry, this is the loss of the algorithm in the teeth. No, I'm messing up something. Some place. There's no empty. There is this T should have gone. So what did we have here? This was epsilon PMT plus epsilon this one. So this is epsilon. Previously we had an epsilon times PMT minus MTPT. Let's write it the same. PT MT. And then there's a smaller order term with epsilon square. P. This was with P, not with PT. empty the absolute value. This is what we get. This minus epsilon is what is over here. These two are what we had got from previous. What is this? This is the loss of the fixed distribution, the loss corresponding to the fixed distribution. Think of P as focused on one expert. It's the loss of the expert. What is this? Huh? So if the algorithm is doing significantly more loss than the fixed, this is reducing it. Each time if the algorithm does far worse than this guy, then this is it's reducing this quantity. That's what's happening in this step. So this step is illustrative of what's going on. And this would have been true even for our original analysis of the MUMW algorithm, where P hat T plus 1 was PT plus 1. Now we have the extra fact, we have that PT plus 1 is actually projection of P of P hat T plus 1. Therefore, we have by the Pythagorean rule, for Bregman projections, D of P PT plus 1 is even smaller than D of P hat T plus 1. Therefore, we further have this fact that D of P T plus 1 minus D P T is less than or equal to this epsilon times so we have sort of a Taylor-like thing. So finally, what do we get? We'll get that D P T plus 1 minus D P1 is less than or equal to epsilon times summation over T PMT minus epsilon times summation over T PTMT plus epsilon square summation over T P. Notice this was the loss function that we cared about. So the loss function L of T, which is summation T PTMT, hence is less than or equal to T1 by epsilon plus summation T PMT plus epsilon summation. But put in all the terms here, and I would have a minus sign, but I'm only going to, that's only going to bound it even higher up. So I'll probably drop it. There's a minus D P hat PT plus 1. I'll just drop it off completely. That's only going to improve the inequality. This is exactly the quantity we got for the other thing also. We got PMT, and the starting point we had got a ln n. That ln n comes, if P1 happened to be the uniform distribution, this would exactly be ln n. So depending on where, so this is a, some sense this is a, it has this, I made a mess of the things again. It has this nicer intermediate in the analysis. There's this nicer intermediate step that is whenever you're comparing against a fixed distribution, whenever the algorithm is performing significantly worse than the fixed distribution, the Bregman projection is sort of this step, the update, this is not the Bregman projection, this is the update, weight update method is getting it back. Is the PT plus 1, P hat T plus 1 is being updated in order to reduce that. Whenever this loss is significantly more than this loss, it's reducing that quantity.